about time. So we might have a couple more folks wandering in, but I know there's also people waiting online. It's a Monday morning, so a second. But just while we're waiting for people to trickle in, I kind of want to know who's here, kind of your general backgrounds. It doesn't have to be like an icebreaker thing that you can just call out, like architect, engineer. Start with Lee. I know you, so I don't think you're out enough, but
We're with design architects.
okay.
So we do K-12 commercial stuff.
Okay, great. All here. Okay.
Yeah.
Great. Well, thanks for being here. And Lee, you were here, I think, last year as well for some of the code trainings. Kind of just a general thing that's happened in Idaho is that we are considering moving to the 2024 code, right? So the lectures today, we've got the 5 of them. So you can definitely rack up your CEUs by the end of the year. And I don't know if you're sticking around for all.
No, we're just sticking for this one.
Just for this one. Okay, great. So
they will all be on our YouTube channel, though.
yes, okay. They will all be posted. So if you didn't get enough of just this, then we'll have all of them up there. But I will cover not just 2018 today, but also what Idaho is considering. Right. And then feel free to just interrupt me at any point. And folks online, we should be able to hear you in the room if they unmute and ask a question too. So to start off with IECC commercial envelope requirements. Appreciate you guys being here. And Gregory's going to come around from our office and take any coffee pastry orders from you all. So if you have preferences, where are we getting it from? Java. So yeah, let us know what will be helpful for you to get through Monday morning. Codes. Now, there we go. Hopefully you know what the Integrated Design Lab is. For those online who might not, just a quick note, we're just upstairs. We're located here in Boise, but we're part of the College of Art and Architecture. Our whole mission is just education. So we're not trying to compete. We're not going to slap your hands and say you're not doing code well enough or try to enforce it or anything like that. We're just educational. When, say, Division of Building Safety comes to us or DOPL and says, hey, we're looking at these code changes, what effect might that have? We will kind of do some research, and we also participate in the Idaho Energy Code Collaborative. And if you guys aren't involved in that, but have gripes about the energy code, please reach out. It's on the website. There's going to be a collaborative meeting on Thursday afternoon, and we really welcome feedback. The hope is to get everybody talking in the room. People that really support industry, that want fewer regulations, people that want more energy efficiency and more regulation, and trying to figure out a compromise. So we're not at each other's throats like the legislature. It is to get industry to work together, figure out what's effective for Idaho, and then bring that to the legislature. Somebody who's been involved in the Idaho Energy Code for a long time is Jerry Peterson, and he always says that energy codes are essentially a backstop, that if you build a code compliant building, it is the worst one you can legally build, right? So this is not like high performance. This is just bare minimum to make sure that we aren't putting together tin shacks with holes in the envelope that people are going to freeze in all winter or roast in all summer, right? For the envelope requirements today, I'm trying to break it up into kind of 3 main areas. One is kind of how much heat escapes or the insulation, how bad the windows are allowed to be, and then how leaky it will be. And just for reference, for everybody. So this whole packet down, and now I've lost track of it. Okay, sorry. There's a large stack of papers still there. We put over there. It did.
Yeah.
Okay, great. Thank you. So the Division of Building Safety this last year voted unanimously to move all the codes from 2018, what we're on right now, to 2024. And that's here. These are the current kind of red line proposals. I will note that if you look online, the version they posted is a little bit out of date. This is the most current version coming from the Idaho Code Collaborative and directly from Justin Touchstone, who's kind of heading up this effort at the Division of Occupational Professional Licenses. So this is what is going to go before the legislature in January. This is not guaranteed to be adopted in Idaho. It was a strong indication from the Division of Building Safety that it was a unanimous decision. So it's possible that it will be adopted, but the legislature has kind of the final say. If it is adopted, it won't be immediate. It will probably be January of 2027. So you've got a full year before this might take effect. So we're in 2018 right now. We're looking at leaping 2021 and going straight to 2024. And that's not just on envelopes, that is, everything. So all the red lines are in there, but that includes all codes essentially. It's the Idaho amendments to the IRC and the IECC. So how do we get just a minimum passing score from the energy code for insulation? Got 3 different ways. One, we can actually, instead of using IECC, use ASHRAE 90.1, which is kind of another organization that also does energy codes, but has slightly different wording and slightly different requirements. The most common one is prescriptive, just looking at the R factors and the U values actually it should be reversed, the R value and U factors for different envelope components. And then the third one is using an energy model. And you have to prove, at least in your simulation, that the building that you are designing is going to cost less to operate than a baseline building. Okay, so those are our kind of 3 pathways for legal compliance. Pathway number 1 is ASHRAE 90.1, 2016. You can't just cherry pick between IECC and 90.1. You kind of have to choose one path or the other. It's similar to the prescriptive requirements. The advantages you get from using ASHRAE as opposed to IECC is that with semi-heated spaces, like maybe garages or warehouses or something like that, you can get away with some lower insulation requirements. But it does have more specific requirements on entryways and vestibules for all other commercial buildings. You also get a little bit more flexibility on air leakage than you do with IECC, and that matters more in the 2024 code than the 2018. Just gonna pause for a minute. I see a few things coming in through the chat.
That's me.
That's you. Great. If something does come through the chat, if you wouldn't mind just monitoring, otherwise, All right, so that's one option. It's basically you just switch over to a different code. I'm not going to go too much into that because a lot of it is going to mimic what IECC is. And so the typical way that you're complying is either R value or U factor. The R value is looking at where are you putting insulation and how big is that insulation. So if we're looking at roofs, we've got a few different requirements depending on the building construction and also where you're putting that insulation. If it's just an attic space or something like that, we use R38. If it's residential, we have higher requirements, R49. And this is just showing our thermal resistance, right? So you can blow in cellulose or something else. You do, shredded fiberglass, and just try to get it to a certain depth, right, in your attics. But if we use it above the roof deck, we actually get away with a lower R value. But that little CI means continuous insulation. So it's not something that we're stuffing in between the rafters. It has to go as a solid layer, some sort of rigid insulation, EPS or XPS or something like that. And the same is true for walls. The reason, I also want to give a little bit of like why do we have these requirements and why are they slightly different, is because the performance is really affected by where you're putting this and kind of where you are drawing your boundary layer, your thermal boundary layer, right? So if we just put insulation above our ceilings, this would be kind of our attic, R38. It's generally not as effective. The further we move our control layers to the exterior of the building, the better the buildings tend to perform when we measure them. So that's why you can see once we insulate above the roof deck, we get away with a lower R value requirement. So you get to use less material because it's generally going to perform better. The main driver behind this is a building scientist by the name of Joe Biscuburek. Probably mispronounce his name every time. But he's been in the field for a long time. And there's a really good resource available that he calls the perfect wall. And he says the perfect roof is essentially the perfect wall turned horizontally. And the idea is we are moving our control layers, particularly thermally, as far out as possible, rather than kind of mixing it within the structure, right? Because you start insulating at the roof deck, you might get some condensation that occurs at the rafters. Same with the insulation above the ceiling. Maybe we have to have some ventilation in there. Things just get simplified and we get more conditioned space when we move our control layers further out. So that's why he calls it kind of the perfect enclosure and looks at not just insulation, but also protecting against water, rain, air leakage, which we'll get into later, water vapor and heat. So if you haven't checked out this article or buildingscience.com, it's a great free resource available to you. I'd say it's worth a Google search when you're having lunch at your desk sometime. If we look at walls, again, how we meet the prescriptive requirements varies depending on the type. If we have a mass wall, again, it's simpler if we have just continuous insulation, and continuous is required for mass walls. If we look at, say, wood framed, we've got two options. One is to use R20, so we could get insulation bats that are just labeled R20 from Home Depot, Lowe's, whatever big box, right? And we just stuff that in between our 2x6 studs. That is kind of why we've moved to using 2x6s rather than 2x4s, is because the 2x4s just didn't provide quite enough depth to get to that full R20 bat. A 2x6 does, and so we can just put in R20 between that, or we could use still, like, say, a 2x4 wall and put in R13 bats, which would fit in there, and then on top of that add another continuous layer of R3.8, so like 1 inch EPS or XPS or something like that, which is usually about R4 per inch. You could also use, something from, Chempatexture or timber, HP, some other, or rock wool, right? Some other form of rigid insulation. It doesn't have to fall. So why do we do that? And why is the energy code kind of pushing for continuous insulation? And I believe it will continue push it that way. Partly, Lee, maybe these look familiar to you from doing your circuit diagrams and physics, right? Another analogy that I think is even better is thinking about it in terms of water flow. But instead of water flowing, we've got heat flowing. And each time we've got something in the river that's going to block that flow a little bit more in terms of our heat. So if our river is just in one channel and we start adding more and more little beaver dams along the way, it's going to slow it down, which is good. But if our river braids and we've got a few different channels, well, we might have a really ambitious family of beavers on one channel. That's really going to slow it down. But somewhere else, maybe the dam broke through, or it's just a bigger stream, and we get a lot of water, or in this case, heat, flowing right through that. And this is what happens with wooden studs, or particularly like metal building studs, right? Sure, we put an insulation batt that's going to slow it down in that channel, but anytime we've got a thermal bridge, essentially, or a lot of flow through another area, we can lose out on a lot of that resistance. So if we think of like a SIPS panel, where it's continuous, right? It's all has to go through kind of the same layers. Then this is a series of like kind of just one channel for the heat to get out. And all we have to do is kind of ramp up one of these resistors essentially, and it's going to slow it down a whole lot. So if we have kind of cladding and then oriented strand board and then a layer of R20 insulation, we end up getting pretty good R value for that. But if we have studs or windows, right, then we end up basically opening up one of these channels. So if we have a window and then some studs and then insulation in between the studs, all of a sudden our total for the wall ends up being kind of a pretty dismal R6. So I love windows, but they do provide problems. And they just have a really big outsized effect. It's this kind of reach in our containment zone. One example, so the book that I've been using in class this year, I highly recommend it. It's by Dr. Allison Bales, A House Needs to Breathe, or Does It? He also has a blog called the Energy Vanguard blog, which is free. It's got a lot of really good installation illustrations on limiting some of the thermal bridging. He gives this example of, you've got an attic, but we've got, one attic hatch to access it. And this would be the true for any commercial roof as well, where we spend a lot of time insulating kind of the rest of the ceiling, but then we've got this one kind of breach where 1% of the area is this door where we didn't put any insulation on it. Put a gasket on it either. And you think, okay, it's just 1%. Our R value for the overall ceiling is going to be, I don't know, R48, R47. It will drop it by a little bit. But just by the nature of the math and the way that resistance calculates when we've got multiple pathways for heat flow, we end up dropping it by a full 9 points down to R40. Right? So any little breach in our enclosure has a huge effect. So that is why the energy code is trying to push for more kind of continuous insulation rather than just component by component. The other way that you can kind of meet the prescriptive requirement, rather than just saying, okay, I've got R such and such between my studs, is to look at the overall assembly, essentially analyze the whole river and all of its braids, and say, what is our U factor? So instead of just specifying, okay, my OSB is R1, my insulation batt is R20, and then I'm adding up, all these different layers. Instead, you do a full kind of thermal analysis, looking at all the bridging that might happen, and you end up with the U factor. The U factor is just 1 over the R value. It's reciprocal. So what do these numbers actually mean? U of 0.09 would be about R11, which is similar to our continuous insulation requirement. U of 0.052 is about R20. The wood frame and metal framed is about R16. So that's taking into account how that thermal bridging might occur, right? When we looked at the wood framed building earlier, it's like, okay, you can put in R20 insulation, but once you look at the thermal bridging, that performance drops a whole lot. So if we achieve at least just an overall R16, then we can meet that. And you can meet that through continuous insulation. You can meet that through spacing your studs further apart, however you want to. This provides kind of more design flexibility for you. And it's something that you can put into ComCheck as well. So this is another kind of just prescriptive way of doing it. And if you think, okay, how do I actually figure out if I've got this wall with all these different layers, what eventual U factor might I get? The IDL does have a free online calculator. It's just an Excel sheet that you can download, and you can put in the different materials, the thickness, the conductivity. It'll show you the R value and then the U factor at the end. So just be aware, if you just go to idlboise.com and look for some of our design tools, we want to make it easier for you. The U factors are also tend to be slightly more lenient. Because again, the Energy Code Council is trying to just push this more like comprehensive analysis rather than just looking like material by material. So you can kind of get away with a bit more if you use the U factor. Okay, there are some exceptions though. We don't need to insulate every single building. If it's going to be a super small equipment building, maybe you've got like a little shed or maintenance garage. Or even say like a little server rack outside, then if you have kind of one server rack that's less than 3 kilowatts and it's a 20 by 20 foot building, this would count where you don't need to insulate it nearly as much. As long as it's not heated to more than 50 degrees and there's less than 5 kilowatts of space heating. So in that case, you can have an envelope of R5 or very, very little insulation. It's a little bit more stringent to climate zone 6. All I'm going to be talking about today is climate zone 5 and 6, which is in Idaho, but obviously these change if you're doing designs in other states and other areas. Windows are particularly rough from thermal insulation standpoint. The Energy Code allows glass of U.38. It looks at the U factor. Maybe it's just to hide how dismal the R value is. I'm not sure. So there are limitations. If we look at kind of what the U factors are for windows, a single pane window, this is not allowed by code anymore, would be R1, right? And so that's a big breach when the rest of our walls should be at R16. The operable windows have a slightly lower requirement, R2.2. And then if it's going to be a fixed window, like we have in this room, then it meets an R2.6 or a U of 0.38. This is not how much sunlight is coming through and heating up the space. This is what happens all night long in this room, right, as heat just flows out through those windows. And you can get this with a double pane window pretty easily. Window manufacturers are aware of these requirements. They manufacture a lot that are at these levels. If you are trying to build something that meets, say, passive house requirements or something like that, you can see that the triple pane windows there tend to have at least twice the thermal performance. But still, an R7 window versus an R16 wall, you're still losing a lot. So the Energy Code does have window to wall requirements, right? Where at most you're allowed to have 30% of your exterior be windows. Or if you add some daylighting controls, then you get away with a 40% window ratio to the exterior wall area. So how do we get the Arthur building constructed in Boise, which is like this full class building? They did that through performance modeling, using an energy model that showed kind of overall energy use and energy costs if it could still achieve efficiency and cost effectiveness, which they did through a more high efficiency HVAC system. Then they could get away with doing a lot of different things with their envelope, including putting however many windows they want. So that is, I think, one of the main drivers for using performance modeling is you get away from this restriction from the energy code that limits the number of windows that you can have in your building. Okay, so that's the third pathway is performance. So you're using energy modeling for lower energy costs, not energy use, but energy costs. You still have to comply with air tightness requirements, which I'll get to shortly, but you get to put in as many windows as you want, which is really nice. And so you can have, different U values for your walls. You can move things around. You're not bound to com check anymore. If you are designing space that has, say, heat pumps versus gas furnaces, though, you do have to factor in that electricity prices might be higher than gas prices. And you have to make sure that you're using kind of local utility rates in your analysis. If you personally don't want to do this energy modeling, well, you lose out on some of that design flexibility, but you can hire an outside consultant to do that. And a lot will do this for like lead modeling or something. So that's one option. Okay. The other part of buildings, kind of the third piece that I need to, okay, I don't need to wrap up right now. That's good. So standing at 10. Yeah. Is again kind of the myth of, do our houses need to breathe? Do our buildings need to breathe? Spoiler alert in this book, no, the building does not need to breathe, but the people inside do. So we need a good ventilation system, which if you stick around, will be what I'll be talking about next. Thank you, Gregory. But we want our building envelopes to be generally tight. There's kind of this myth that, well, if we just kind of have infiltration, that'll bring in enough fresh air, but there's no control over that. And so that can bring in smoke, pollen in a house, radon, and in Idaho homes, for new construction for a 3,000 square foot home, what typically happens is you've got all these little cracks everywhere. And if you add them all up, ends up, this was something that Gregory put together, which I really appreciate. Most homes in Idaho have an ACH of about 4. This is essentially a cat door that stays open all year long that you can never actually close if you start adding up all those potential leakage areas. Right? Or think of like a window that you can never quite shut. That would end up being about this size. And how much air blows through that window? Well, it depends on outdoor temperatures, wind, and can you filter out smoke, or maybe it's coming through the walls next to some mold or something like that. You can't. And the other downside of it is that, particularly in commercial buildings, if we think, okay, we're spending all this money on HVAC to keep this place comfortable, but then we've got this window that we can never close, it ends up being about 30% of our heating load. So a third of the heating energy that we're putting into our building is just getting lost, right? It's just being sent out into the world. Maybe it makes some squirrels and birds happy right around the building, but inside we're kind of still paying that penalty for it. So there are requirements in 2018. You're looking at kind of the exterior surface area to not exceed 0.4 cubic feet per minute per square foot of exterior area when you pressurize it. In 2018, you're kind of just adding up all the different materials to make sure that they're not exceeding this requirement. 2024, we actually start testing for that in commercial buildings. And the requirement also drops. Residential, we measure it differently. We measure it in air changes per hour, but it kind of tracks these two. In Idaho, we used to have 5 air changes per hour, and you have to test 1 in 5 homes. We've removed that testing requirement, and now we're just trying to meet that 3 air changes per hour. Okay, so there's 2 methods in 2018 in current Idaho code. One is to do an actual test. The other is to do this kind of prescriptive method where you're looking at the different air barriers, materials, assemblies, and windows. So there's also requirements in terms of where you're sealing, doors and access openings, stairs, loading docks, vestibules, and recessed lighting. See if I've got, don't know that I have it here, but this does not necessarily mean that you are wrapping your building in plastic. There's a big difference between an air barrier and a vapor barrier. So materials that count as an air barrier would be OSB, it could be masonry, it could be your insulation layer if it's EPS or foam, it could be Tyvek, or we often see zip sheeting systems too. There's a list in 2018 IECC with like 16 different types of materials that all work as air barriers. As long as you kind of list them in 2018, you're good to go. There's not a lot of commissioning done on it to check if it was installed correctly. And that can be a problem, right? Because you could put on some Tyvek or something like that. Somebody else comes through, makes a change, or maybe the sill plate isn't properly sealed. There's no gasketing there. Nobody comes back through to actually check it. It's just kind of taken on faith that your contractors are doing a good job. Turns out that's not always the case, right? So with 2024, there is now requirements for doing testing in commercial buildings. Depending on the building size, you're either testing a portion of the building or the whole building itself. You also have to document not just the components, but all the details that you're putting in for joints, interconnections, penetrations through the air barrier, and the methods for sealing, like your caulking, your gaskets, etc. You also have to ensure the continuity to say, well, it's not just that I put an air barrier on my wall and then I put one on my roof. You have to show where you're sealing between those two, right? Again, Dr. Burek, someday I'll meet him at a conference and he'll tell me how to pronounce his name. Uses something that is very simple that I really like that I had my students do this year called the red pen test, where you put in your wall and roof and foundation details, and you just take a red pen and draw along there, where is my air barrier line? And is it continuous? And if I have a gap in between the two, how am I going to solve that? Right? This is what 2024 is now asking architects to do. Again, it's a new requirement. It's a new portion of your construction documents that you're going to have to include. There's also testing that is now going to be required. So you have both kind of like testing and then performance verification, where somebody's out on site to look at different stages of construction and make sure things are put together in the way that you detailed. So if you haven't done commissioning or testing on a commercial building, something that has been more often done in residential than commercial, I would recommend finding somebody that does that, because it would, and developing a good relationship with them, because it will be, if adopted, a new requirement in Idaho, and there's going to be a much higher demand for it. There's always the possibility of amendments to the code. So if this next year you feel like, whoa, this is way too much, we can't find the technicians that we need to, that's when you come to the code collaborative and say, we should really, pull our foot off the gas on this particular requirement and maybe have an exception for Idaho. The reason that IECC is moving towards this testing is just for this verification, right? Rather than just taking it on trust that it's put together right. There was a study that IECC did, the Code Council did, and buildings without an envelope consultant, is that here? Yeah, 40% of buildings constructed without a consultant exceeded their leakage requirements. So nearly half of them just weren't even meeting what they were supposed to. Every building that they surveyed with an envelope consultant had a leakage like 30% below the legal requirement. So they were far surpassing what they needed to do, which again really cuts down on your heating loads. So if you haven't worked with an envelope consultant yet or haven't done envelope commissioning, I highly recommend starting. It will also affect like your HVAC size. A lot of engineers will put in extra safety factors, say, okay, well, it's going to be so leaky in the winter and I'm going to have an extra large boiler or something like that. If you have an envelope consultant and you end up with a leakage that you have a far tighter building, a higher performance building, you get to downsize some of that equipment, which can save on capital costs. And that can be very helpful. If they just keep the same size of equipment and just assume it's a leaky building, what you'll have is equipment that is too large for the space and just cycles on and off, which is going to basically rush in a whole bunch of hot air, then shut off. It's going to be very disruptive, and it's harder on the equipment rather than something that's right size, which is slow and steady. Okay, so if you do envelope commissioning, which again in 2024 will be a requirement, right now in 2018 it's not, but you do get 2 lead points for this. So Lee, this might be helpful for Idaho Army National Guard or any other federal building that still has lead requirements. So 3 lead points in addition to code compliance. Great. The first building in Idaho, commercial building that went not just net zero, but net positive, still producing more energy than it uses, is the 20 Mile South Farm. There is a case study available on it at betterbricks.com. Anybody familiar with Better Bricks? No. I should have said this at the very beginning. The reason that we are providing these free and resources for you is because we are sponsored by the Northwest Energy Efficiency Alliance, which is funded partly by Idaho Power and other Northwest utilities to kind of just reduce energy consumption so that we don't build more power plants. Right? The idea is cost-effective efficiency. And so they have a branch of educational materials called Better Bricks, and it's an online resource that's free. And they have they have a number of different case studies, but they have one particularly of 20 Mile South Farm. And this achieved extremely high envelope performance. Partly it was reducing infiltration, but it was also continuous insulation there as well. So very little heat kind of leaks out of it during the winter or cool leaks out of it during the summertime. And with the solar panels they have out there, it ends up, I think I said, producing more energy than consuming. So it's pretty neat. So some of the things that they specified was to make sure that they kind of sealed any of those cracks, so we don't have. It also helps with like bugs and dust getting into places. The less infiltration we have, so that reduces maintenance times. Taping and sealing the sheathing, and then specifying on the mechanical side ultra low leakage dampers. So anytime those are closed, they've actually got the rubber or foam that's going to close that rather than just two metal pins that mostly close but still some smoke gaps. This is more on the residential side, but I wanted to mention it anyway. Like I said, we used to have testing, but we don't anymore. Partly because we have rural jurisdictions, Grangeville, Riggins, Salmon, Idaho, where getting somebody to come out and do the testing was a huge burden. They weren't available, they couldn't find somebody, or they just had to wait too long for a blower door test. So we removed that requirement. So no blower door testing is required. Certain jurisdictions still do prefer that method of compliance, and City of Boise is one. So most new homes constructed in Boise, inspectors like to have a test done so that they can kind of verify the performance. But a lot of others, it's just left up to the inspectors. And the inspectors, if you look at the code book, 2018 IECC book, it's a very long list of text, if you will, on the specific ways of detailing and everything like that. Honestly, my eyes glazed over a bit. My hope for codes kind of comes from my mentor, Ken Baker, who used to run the lab and has been in charge of codes in the Northwest for a long time. And he advocated for progressively effective codes, not just more stringent, but codes that are just simpler, easier to understand, and easier to comply with, right? So we worked with Jerry Peterson, we being Integrated Design Lab and the Northwest Energy Efficiency Alliance, on what are like the 9 or 10 biggest gaps in construction that tend to occur in homes. Where do we get the most bang for our buck, right? If an inspector is going to come in, instead of this long list, how can we simplify it to just be, like I said, kind of very effective, so that instead of doing a blower door test, they just check off the major items, and then we hope that we get to an ACH of below 3, maybe 2 or so. And these are we wanted to be less than 10, so we came in at 9. It's pretty simple stuff. Gasketing access doors, like into the attic, sealing framing spaces, sealing our recess lights to the drywall or sheetrock, HVAC registers, top plates, narrow cavities, and then going up after electrical and plumbing to just kind of put in some big flex or some other splits in there. Gregory, who was in here earlier, helped on this to actually look at other resources from Pacific Northwest National Lab and Energy Trust of Oregon to put in little thumbnails for each of these and have this kind of simple guide with an explanation of what should inspectors look for. It's free. It hasn't been posted to our website yet, but it will be over this next year. So if you want, actually, I'll save one for Lee. But yeah. The hope is for kind of simpler compliance and just make sure we're kind of just checking through the boxes of this. And if you look through the red lines from Doppel and DBS that I gave you earlier, they have actually changed the language for residential infiltration testing to just match these time. They work together on it. National Association of Home Builders really liked this checklist as well. It simplifies their jobs. It simplifies the jobs of inspectors. So I'm excited about this. So if the legislature adopts it, this will be kind of the new checklist for Idaho homes. I want to make sure that there's enough time for questions and to get set up for the next lecture. The main takeaways from commercial envelopes. One is, instead of just layering different materials based on the R value, I would encourage you to try to use the U value, the U factor method. It offers kind of more flexibility, different designs for the envelope, and it's just a better indicator of performance as well. For windows, if you want more than a 40% window to wall ratio, or even just higher than 35%, all those without the extra daylighting controls, then use the energy model method. I am a fan of the performance method, not just because we do a lot of energy modeling at the Integrated Design Lab, but because it's trying to push towards, again, kind of simpler, more effective means of assessing our buildings even before they're constructed, and to show to the owner and especially the tenant, hey, once you construct this, not only is it maybe saving carbon or emissions or anything like that, but it's saving on cost, right? It's saving on your energy costs per year by at least 15% over your minimum kind of baseline building. And then when it comes to infiltration, be prepared for 2024. Even if you're not building in Idaho, there's requirements in the 2021 code. So any jurisdiction that's on the 2021 code, or 2024. I think Montana is adopting the 2024 code. I know City of Phoenix has. Oregon and Washington and California along the coast, they've got their own energy codes. They're on their own journey. I'm not going to get into those. But they typically kind of track with the IECC. And more they're pushing for this, not just trust like in 2018, but trust but verify in the 2024, of actually verifying that the materials are detailed properly, that they're constructed properly, and that you're actually doing testing at the very end of this. 2021, the testing requirements are only for certain types of buildings, multifamily, and buildings that are smaller than 5,000 square feet and bigger than 50,000 square feet. There's kind of this weird gap in the middle. 2024, it's kind of just all commercial buildings. So if that comes, just kind of be prepared for that. And those are kind of the big takeaways for today. If you have questions, feel free to email me directly. If you want to be involved in code conversations, which sometimes are so boring, but they are impactful, right? And even if you just want to say, hey, I've got this one comment, I've got this project, and it was really a concern getting through this particular section of the code. The more that the collaborative with, and also the Division of Building Safety hears that, the more they can respond to it, to really adapt things specifically for Idaho. The goal of the Idaho Energy Code is not to make your lives miserable. It is kind of consumer protections, right? To make sure that people don't move into a building and are suddenly uncomfortable, unhealthy, and have super high energy bills. The more we can kind of limit the documentation and compliance, I think the better. But who really loves bureaucracy? So the more we can kind of simplify this and streamline this, and I think one way is through the performance modeling. Another way is like that U factor method. The easier it is to provide a building for your clients, for the occupants, that meets not just, their shelter requirements, but also their health and their bottom line. I'll go ahead and stop there and take any questions you guys have. Folks online are also welcome to ask questions too.
What software are you using for performance modeling? Are there specific programs or requirements?
Yes, so it's not software specific, but it does have to meet certain mathematical models, essentially. Most of them in the US run on the engine of Energy Plus, but it's got a ton of different front ends. Some are free, some you have to pay for. At IDL and kind of the research grade software that we use is Open Studio. And there are some firms that use Open Studio, Cushing Terrell being one. I think Group 14, they're out of Colorado. They also use Open Studio. But you can use Revit's tools, Insight. You can use IECC, that's used more in Europe, but we did see it used in Idaho this last year. Any building that tracks kind of hour by hour weather rather than just like single point in time, like one July day, one January day. Instead, it's doing kind of this full year analysis hour by hour. And so eQuest, I think, counts as well. I don't know if you have to pay for that one. Code Tool I used to use in class, but they are changing their model. They're not their model, but their market structure, I guess.
Their business model.
Business model, thank you. To be less like architects using it individually and more as kind of like outsourcing to their firm to kind of do it all for you. Yeah. But you've got a variety of different options.
Is there like a resource where it lists out what they'll accept performance-wise? As far as like you said, it's the math behind it and
Right.
the hourly. Do they have a list of?
That's a good question. It would be anything that meets ASHRAE 90.1 Appendix G. I think if you just Google that, honestly, software that meets ASHRAE 90.1, you will find a list. And ASHRAE might have published that as well. So do you know of another place?
IBIPSA,
IBIPSA?
yeah, they're best. Building energy simulation. I'm forgetting what the T stands for, but it's their directory of all simulation software program. So acoustics, water, air, light, thermal. So it has everything, but just on the left side of it, there's a filter on the website. Use that. It'll tell you like, I want HVAC, or I want lighting, or I want daylighting, and it will filter all of those.
What was it called?
BEST.
EST. Building energy simulation tools. I think that might be what the T stands for.
IBIPSA is the International Building
Performance Simulation Association.
What was the other one that I failed to mention? Rhino and Grasshopper. Grasshopper, ladybug. But it can be really cool. Yeah.
Cool if you know how to use it.
If you know how to use it. That's the thing with a lot of these is that kind of the more you pay for, the easier it is to use. And the free ones, there's pretty steep learning curve.